Aerial refueling is governed by a strict volumetric constraint. Every cubic meter of fuel required for the mission occupies space that would otherwise hold cargo or personnel. Historically, legacy platforms like the KC-135 Stratotanker solved this by modifying the internal fuselage. Engineers had to install massive auxiliary fuel bladders directly inside the main body of the aircraft. This created a severe operational penalty. Filling the fuselage with fuel essentially turned the aircraft into a single mission asset, leaving almost no physical room for heavy freight or troop deployment. The Airbus A330 multi-role tanker transport, also known as the MRTT, was engineered to bypass this specific volumetric bottleneck. The platform has captured over 90% of the tanker procurement market outside the United States. Airbus achieved this market position without designing a bespoke military airframe from the ground up. Instead, the MRTT architecture exploits the high structural margins and native internal volumes of its commercial airline foundation. To see how the design works, we start with the standard civilian A330-200. Commercial long-haul jets require massive fuel capacity to cross oceans, so the native wing and center wing tanks act as enormous integrated reservoirs. These hold 111,000 kilograms of fuel without external modifications. This capacity is so large it performs high-volume refueling without auxiliary fuselage tanks. Keeping fuel strictly inside the wings leaves the fuselage completely open, preserving the full volume of the passenger deck and lower cargo holds. This space carries 380 troops, 130 medical stretchers, or 8 military pallets and containers. This brings the total non-fuel payload capacity to 45,000 kilograms. For context, 45,000 kilograms rivals the transport capacity of some dedicated heavy strategic airlifters. By separating fuel volume into the wings and cargo into the fuselage, the MRTT maintains 100% dual-role capability on every sortie. A major engineering hurdle in tanker conversion is mounting heavy refueling pods to the outer edges of the wing. Pods create significant aerodynamic drag and physical mass, which usually requires extensive structural reinforcement to prevent the wings from buckling under the load. Airbus solved this by using structural commonality. The twin-engine A330 shares its wing architecture with the four-engine A340 airliner. Because of this shared design, the A330 wing already contains reinforced mounting locations meant for a heavy outboard engine. These dormant mounts include pre-existing internal routing for high-pressure fuel piping. Airbus simply mounts the Cobram refueling pods directly to these reinforced hardpoints. This avoids an expensive and heavy structural redesign of the wing. This commonality also simplifies production, as the aircraft can be built on standard commercial assembly lines before moving to military conversion. The A340 Heritage provided the exact structural strength required for a military tanker, integrated into the civilian structure from the beginning. Allied air operations face a logistical challenge. Different aircraft utilize incompatible refueling methods, either a flexible probe and drogue or a rigid flying boom. To ensure interoperability across various national fleets, the MRTT utilizes a modular tri-system interface. System 1 is the Airbus aerial refueling boom system under the tail. This rigid, high-flow system services receptacle-equipped aircraft like heavy bombers or F-35s. System 2 consists of the Cobham 905E under-wing pods, which use hoses to service smaller, probe-equipped fighter jets. System 3 is the Cobham Kiddo 5E fuselage refueling unit, which deploys a central line hose for heavy, probe-equipped transport aircraft. Managing 3 separate systems required a shift in avionics. Legacy tankers required a boom operator to physically look out a rear window. The MRTT replaces the window with the boom-enhanced vision system, allowing operators in the cockpit to direct the refueling using high-resolution 3D cameras. These digital systems and the tri-system architecture allow a single MRTT to sustain refueling for entirely different national fleets on a single mission. This interface enables the MRTT to act as a universal node for fluid transfer across combined NATO fleets. Because the platform is based on a commercial jet, it faces a specific supply chain reality. Commercial production of the original A330-200 ended in 2018. Modernizing a military platform often requires a multi-billion-dollar development cycle spanning a decade. Airbus avoided this by transitioning the existing military hardware onto the updated commercial A330-800 platform, known as the MRTT Plus. The upgraded MRTT Plus architecture seamlessly integrates the massive, highly efficient Rolls-Royce Trent 7000 engines found on the modern commercial Neojets. As shown here, these updated engines and aerodynamic refinements result in an 8. Operating a platform based on a commercial airliner also allows these nations to tap into a global civilian parts supply chain, lowering maintenance costs. While traditional tankers often sacrificed payload to achieve mission range, the MRTT delivers both by exploiting the native volume of its foundation. The A330 MRTT maintains its global position because it proved that an efficient military tanker is engineered by optimizing the architectural margins of existing commercial aviation.